Does this sine curve show a transverse wave? Not necessarily. It could be a displacement distance graph of sound. A graph can show how a quantity varies without showing a medium's physical shape. Classify a wave by comparing its oscillations with the direction that the energy travels in. On this string, the disturbance and energy travel right, while each marked point moves up and down about equilibrium. Displacement is perpendicular to the energy transfer, so the wave is transverse. Transverse does not mean vertical. Turn the string and both directions turn. The right angle is what matters. Electromagnetic waves are also transverse, but the field oscillates rather than particles. All electromagnetic waves travel at 3.00 times 10 to the 8 meters per second in a vacuum. We call this the speed of light. Now, use the same direction of travel, but let each particle move backwards and forwards along it. The displacement is parallel to the direction of energy transfer, so this wave is longitudinal. Sound moving through air is the key example. Air molecules oscillate about equilibrium positions, while moving regions of high pressure, called compressions, and low pressure, called rarefactions, carry the disturbance onwards. Freeze the particle pattern and plot each particle's displacement against its equilibrium position. The sine curve is not the shape of sound. Positive displacement means forwards in the direction of propagation, negative means backwards. At this downward zero crossing, particles behind have moved forwards and those ahead have moved backwards. They close the gap, so this is a compression. At an upward zero crossing, the particles move apart, so this is a rarefaction. That places compressions and rarefactions on the axis crossing, not at the crests and troughs. The crest is actually where particles have the maximum forward displacement, and nearby particles have shifted by nearly the same amount, so the spacing and pressure are virtually normal. A trough is a maximum backward displacement and also has pretty normal pressure. Adjacent compressions are one wavelength apart, as are adjacent rarefactions. A compression and its nearest rarefaction are a half wavelength apart. This crossing rule follows the sign convention shown. Reverse the positive displacement arrow and it reverses too. The rule is simple. Oscillation perpendicular to energy transfer means transverse. Oscillation parallel to it means longitudinal. The curve alone cannot decide. Polarization tests that difference. In unpolarized light, the electric field oscillates in changing direction perpendicular to propagation. Polaroid has a transmission axis and passes only the field component along it. The output is plane polarized, one fixed oscillation direction across the entire ray. Add a second filter as an analyzer. Parallel axis gives maximum transmission. Rotating it reduces the intensity. Crossed at 90 degrees, you get 0 in the ideal model. This filtering needs alternative directions across the ray, so only the transverse waves can be polarized. Sound in air is longitudinal, with every displacement along propagation, so it cannot. The result of this is that light can be polarized because light is transverse, but sound cannot be polarized because it is not transverse. The Cambridge International spec also uses Malus law, I = I₀cos²θ. I₀ is the intensity of the already plane polarized light arriving at the analyzer, and θ is the angle between its polarization direction and the analyzer's axis. At 45 degrees, half passes. At 90 degrees, in theory, none passes. For a series, apply the rule one filter at a time. Each output aligns with that filter's axis. Some applications use the same geometry. For example, a receiving aerial is strongest when its rod is parallel to the incoming electric field oscillation. A metal grill does the opposite job. Rods parallel to that field block microwaves most strongly by driving currents along the metal. So compare two directions. Perpendicular means transverse and it can be polarized. Parallel means longitudinal and it cannot. Next, we'll see what happens when two waves traveling in opposite directions superpose to form a stationary wave.